Uh, hmm. Good evening, ladies and gentlemen. This is Professor David G. De Los Reyes again. My topic for tonight will be a continuation of my long video format topic, uh, DC circuit. And for the DC circuit, I am now on lesson number 22. We are almost done with the so-called DC circuit. The title of the topic for tonight will be Nodal's theorem. So we are done with the different theorems like superposition, Thevenin's, Norton's, Kirchhoff's voltage law. For tonight, I will be discussing Nodal's theorem. Nodal's theorem and how to compute for the current passing through a resistance RL in the circuit. Okay, let's proceed. The subject matter for tonight, long video format topic on my channel. This is Professor David J. De Los Reyes. This is circuit lesson number 22. The title of the topic will be Nodal's theorem. For Nodal's theorem, the so-called simplified formula on how to compute for V sub L will be this. And for the computation of the current, it is represented by this. Okay, I will try to read the concept, then later on we will try to derive this formula here. And how come for Nodal's theorem, this will be the required equation in the computation of V sub L, meaning V sub L is the voltage across this. Okay? If we know the voltage across this, and we are given the value of RL, we could compute for IL. So by using Nodal's theorem, this will be the required equation. Okay, I will try to read the Nodal's theorem. For n sources of EMF or voltage sources connected in parallel connection, supplying a common load, the formula on how to compute for the node voltage, V sub L is actually the node voltage. That's why there is a term nodal here. Node. Nodal node. Okay, to compute for V sub L, the node voltage. Okay, I will try to read the formula. It will be an E1 over R1 plus E2 over R2 plus ... The last part will be E sub N over R sub N. The resulting denominator will be the summation 1 over R1 plus 1 over R2 plus ... The last part here will be 1 over R sub N plus the load RL, 1 over RL. That is for N, if the value of N is given. So for N is equal to 2, this will be only up to R sub 2. For N equal to 3, this will be only up to R sub 3. So this is a variable thing. So this is actually a general equation on how to compute for V sub L. The legend of the, what you call this, the terms on the formula or on the equation are actually this one. V sub L is the node voltage, node. E1 and E2 are actually the voltage sources. R1 and R2 are actually the resistances. Resistances meaning the internal resistance of each voltage source. For E1, there is an internal resistance R1. For E2, there is an internal resistance R sub 2. So these R1 and R sub 2 are actually internal resistances of the voltage sources. So in here, I just specify R1 and R2 are the resistances, internal resistances of the voltage sources. And R sub L is the load resistance. RL is actually the load, the common load. Okay? And to compute for I sub L, we will be using this equation here. Okay? Upon the computation of P sub L, I sub L now will just be simply B sub L over R sub L. We have computed for B sub L by using this formula here. And the denominator is actually the value of the resistance R sub L. So I sub L in general will be B sub L over R sub L. So for Nodal's theorem, okay, just remember this equation here, but take note of the value of n. Because the value of n could be 2, could be 3, it could be 4, it could be 5. So this is a variable thing. And for I sub L, upon the computation of B sub L by using this, taking note of the value of n, I sub L now will be B sub L over R sub L. That's Nodal's theorem. This is actually very near to the term node. Nodals or node. That's why if there is a node, we see that the theorem used in this computation is actually Nodal's theorem. Okay, let's try to bring out the figure. To simplify the so-called, I will try to look for my camera. To simplify the derivation of this, we will just consider for the meantime two voltage sources, okay? Voltage source number 1, voltage source number 2, they are in parallel, supplying a common load RL, okay? Just to simplify, what you call this, the derivation for the meantime. This will be R1, R2, this RL. The current emanating from voltage source number 1 is I1. The current emanating from voltage source number 2 is I2. And the total current that passes through load RL due to E1 and E2 will be simply designated I sub L. So in here, the concentration of the problem is pi I sub L using Nodal's theorem. It's not Thevenin's, it's not Norton's, it will be Nodal's theorem. So this is the concept of the Nodal's theorem. Okay, let's proceed with the continuation. To visualize the so-called derivation of the formulas, we'll try to cut the circuit like this. We'll disconnect here. And we'll disconnect here. So upon the disconnection, hold on. Upon the disconnection, we'll cover this one. We'll refer this one as figure number 1. That's it. We'll cover the left side and the right side. We'll just consider the middle part, and that will be figure number 2, this one. We consider this portion here. We'll just consider the right side after the disconnection. This figure here is actually referred to as figure number 3 with all the proper designations. Okay, proper designations. We just copy the designation here like this one. This is E1, this is R1, I1. The added thing here, this B sub L here. This is B sub L. The node voltage, B sub L. This is B sub L. This is B sub L. That's the added thing. That's why Nodal's theorem, right? The voltage across this is same as the voltage across this part here. Same as the voltage across this. Okay? And we refer that one to B sub L. The node voltage. Okay? Let's try to bring out the so-called, and the legend, B sub L is the node voltage. Okay, let's try to bring out the different equations and how to compute for B sub L. So considering figure number 1, we will take the summation of the voltages and they should be equal to 0. So E1 minus the drop here minus the drop here should be equal to 0. Okay? There are values here, but we try to compute for I sub 1. I sub 1 will be E1 minus B sub L over R1. That will be equation number 1. That's pure algebra, right? After taking the summation and simplifying, we will compute for I1 as a function of the other terms. I1 will be E1 minus B sub L over R1. That will be equation number 1. Consider figure number 2. Plus I sub L R sub L minus B sub L equal to 0, or just simply the current passing here will be the voltage across this divided by R sub L. So we got equation number 2. I sub L, the current passing through I sub L will be the voltage of the node voltage V sub L divided by R sub L. That will be equation number 2. That's the reason why I bring out this free body diagram so we could visualize when we derive the resulting equations. Okay, I will try to move this one. Consider figure number 3. Again, taking the summation of voltages and they should be equal to 0. Plus E sub 2 minus the drop here minus the drop across this, which is the node voltage, and this should be equal to 0. So if we try to compute for I sub 2, we manipulate this one, that's just pure algebra. It will be A sub 2 minus B sub L over R sub 2, and that will be equation number 3. Okay, so we got 3 equations already, 1, 2, 3, involving I sub 1, I sub L, and I sub 2. The third free body diagram will be this portion here. On this junction, okay, we'll try to reconnect. Right? There's a current passing or entering node A, right? That will be I sub 1. And there's a current also entering node A coming from A sub 2, that will be designated I sub 2. And there is a current leaving node A, okay, and that will be designated I sub L. It seems it's just like we disconnect here, and we disconnect here, and we bring out this one, right? So what comes out is this. The current entering node A, Nodal theorem, right? Node A. Node or junction, they are synonymous, right? This here is a junction or node, that's why Nodal theorem, right? The current entering node A will be I1 and I2, and the current leaving will be I sub L. So if we take the summation of the current considering node A or junction A plus I sub 1, current entering is plus, I sub 2 is also entering, leaving is actually I sub L, so this is minus I sub L, and they should be equal to 0. So this is actually equation number, we call this equation number 2. So what do we do now? We will take the value of I sub 1, I sub 2, and I sub L emanating from equation number 1, 2, and 3. We place it here. I sub 1 will be E1 minus B sub L over R sub 1, and this is. I sub 2 is actually E2 minus B sub L over R sub 2, minus B sub L. I sub L is B sub L over R sub L, and this should be equal to 0. And if we try to simplify this one, this is now pure algebra. The expansion of this one are actually 2 terms. The first one is E1 over R1, it is this. This one, the first term will be E2 over R2, it is this. The second part of this, it will be minus B sub L over R sub 1, we transpose it to the right. Okay, so it will now be plus. The second part of the expansion of this will be minus B sub L over R sub 2, it's also negative, we transpose it to the right. And this minus B sub L over R sub 1, we transpose it to the right. So if we transpose this portion here to the right, there is a common factor B sub L. So this should be multiplied by the quantity 1 over R1, 1 over R2, plus 1 over R sub L. So if we try to compute for B sub L will be E1 over R1, plus E2 over R2, plus this portion here. The reciprocal values, 1 over R1, 1 over R2, plus 1 over R sub L. And this equation here is actually the node voltage if the value of n is equal to 2. Okay? Like what I said, to simplify derivation, we consider for the meantime the value of n is equal to 2. This voltage source number 1 and 2. N here is actually equal to 2. Right? So the formula on how to compute for the value of B sub L, if the voltage sources is n is equal to 2, it will be given by this equation here. So if there are voltage sources which is greater than 2, it could be 3, it could be 4. The general equation now on how to compute for the node voltage will be given by this one. It will be E1 over R1 plus E2 over R2 plus the last part here will be En over Rn. Okay? So this is a general equation now. This is 1 over R1, 1 over R2. This is plus. Okay? 1 over R sub n. The last part will be 1 over Rl. So this equation here is actually this one. Sorry for that. This equation is actually this. Okay? That's the derivation of the node voltage as a function of n is equal to n. It could take any value of n. N equal to 1, there is no such thing as n equal to 1. At least n will be equal to 2. Could be 2, it could be 3, it could be 4, it could be 5. So this is a general equation in terms of the number of voltage sources. Okay, that's it guys. That's Nodal's theorem. So the main concentration of Nodal's theorem is actually if the circuit is actually parallel and we are asked to compute for the current passing through a common load. It depends on how many voltage sources. The formula on how to compute for the voltage across this will be given by this. And as soon as we could compute for the voltage across this, the current passing through this common load now will be the voltage across this, which is the so-called node voltage. That's why it's Nodal's theorem, divided by RL. This is represented by this. Okay, that's it. That's the concept of Nodal's theorem and the derivation of the formula of the node voltage. And upon the computation of the node voltage, we could compute for the required current. Okay, for those of you who would like to subscribe to my channel is at youtube.com/@ProfDavidJ.De If you want to share it, please click share. I am assuring you, you will learn something from it. Okay, good evening from Los Angeles. This is Professor David J. De O, sige na.